This is the first video of this section on improper integrals. I'll start with an example to show you the type of problems we want to solve, and I'll show you why we can't really do it, but the geometry will tell us how to define these new types of integrals. So we've been finding areas of different regions. Let's try this one. I have a top bound of y equals 1 over x squared and a bottom bound y equals 0. And I'm going to look from 1 on. So on the right of x equals 1. Alright, so this region looks like this. I have y equals 1 over x squared. I have x equals 1 right here, and I'm looking at the region between the axis and this right here. Now usually what we would do is we would find an intersection point, but there are none in this case. 1 over x squared cannot be 0. And so really what the area is, it's the integral from 1 to infinity of top minus bottom so integral from 1 to infinity of 1 over x squared dx. All of our definite integrals always have finite bounds underneath and a finite bound on top. Otherwise, our definition with Riemann sum doesn't make any sense. Delta x cannot be infinity minus 1 divided by n. That would still be infinity. So here, it's not clear what this integral means. We want it to be the area of this region, which is not bounded but still might be finite, as you'll see. So I'm going to use this idea of looking at this area to figure out what this should mean, what this integral from 1 to infinity should mean. So that's going to be my idea. So I'm going to look at regions that look like this but are bounded. And then I'll take a limit of these areas for regions that are closer and closer to the one I care about. So consider the regions. I'm going to start the same way. I'm going to still have my y equals 1 over x squared. I'm going to still start at 1. But instead of letting it go forever, which was the reason I couldn't complete this computation, I'm going to stop it somewhere. I'm going to stop it at t. So I'm going to look first at this area here, not from 1 to infinity, but from 1 to t. This is a computation that we can do. It's a finite interval, so I'm going to use the definite integrals that we're used to. And then what I'll do is I'll send t to the infinity afterwards. Alright, so I'm going to call this area A of t. It depends on t. So according to the same reasoning, it's going to be the integral from 1 to t now, or top minus bottom. So top is 1 over x squared, bottom is 0. So I'm going to integrate x to the minus 2. That's going to be x to the minus 1 over minus 1 from 1 to t. I'm going to plug in t and plug in 1. At t I get this, at 1 I get this. So all in all, this integral here, this pink region, has area 1 minus 1 over t. So if t is 2, I get 1/2. If t is 4, I get 3/4. If t is 25, I get 24 over 25. But we don't care about 2, 4, 25. We care about infinity. So a, which is the region that keeps going forever and ever, that a should be the limit of these. So a is the limit as t goes to positive infinity of at. So it's the limit of these so we'll get the limit of 1 minus 1 over t. That's 1 minus 1 over infinity. This will be 0. And I get a nice finite area of 1. So even though my first region was not bounded, I still get a finite area, which is cool. And I get it from looking at these truncated region that stop at t and then letting t go to infinity, not using Riemann's sums, but after you've computed these, then you will apply the limit. All right, so what did we learn from this example that we'll use in the next video? To define all of these integrals with infinity bounds. So here's the lesson. If I have the integral from a to positive infinity, this is not a definite integral like the ones we're used to. I'm going to change that top bound, that's infinity for a finite value, represented by a variable, and then I'm going to use a limit to send that variable to positive infinity. That's what we learned in the last example. That's what we'll use to define improper integrals in general.